Okay, so now that we have the time evolution operator, let's talk about a special type of states called stationary states. Let me see if I want to talk about this first. Yeah. So do you remember stationary state? We talked about stationary states in the context of the Bohr atom. Okay. So remember the Niels Bohr, conjectured that the electrons in a hydrogen atom are in a state whose energy does not change with time, right? So these were non-radiating states, remember? Because that was an ad hoc assumption, okay? So what does it mean? So that was like in the old, classical, so old quantum mechanics, what does it mean in terms of, say, in quantum mechanics, right? So if you are going to go to quantum mechanics, let's make an analogy. Okay? And the analogy that we have is of a classical string. So for example, if you have a taut string, and it's vibrating in a sort of standing wave, and suppose that we can ignore the energy, the dissipation of energy due to friction, then the standing wave will have some form like this. It'll have a profile which is space dependent and another profile which is time dependent, right? So for example, we have the string attached between here and here. And what will happen is that, depending, it'll have something like this. But the string that'll be the profile function, right? This is going to be the profile or the envelope. But in every point in the string is going to oscillate up and down. And that'll be given by this sine function, right? For this point, these points, the nodes are not, but all the other points are oscillating up and down, right? So this is our classical notion of what we expect as a stationary state. So a stationary state is not something where things are not moving. They're moving, but they're moving in a way that, the energy is not changing, and there is some oscillations. So, of course, in quantum mechanics, we are not allowed to have this sort of time dependence, right? That's when we discovered the Schrodinger equation, we saw that. So in quantum mechanics, the analog of this is going to be if we have a wave function psi of x of t. So this is capital Psi. We can write it as a spatial profile and a time oscillatory part. Now, if I put this into my Schrodinger equation, then what I get is that the time dependence drop out, right? Because if I IH bar d of psi by dt minus h squared by 2m. So we get h bar omega e to the power minus I omega t psi is minus h squared by 2m. Of course, here the time part just factors out, minus I omega t, and so we have these d squared psi by dx squared. Same happens over here. Okay, and then we can just factor those things out. So as a result, what we get is that time-independent Schrodinger equation. And suppose that we have solved this equation. So solution is, say, psi of e of x. Then the time-dependent, how does this state evolve in time? Well, by our assumption, it's basically e to the power minus I e over h bar t psi e of x, right? And so these states are called stationary states. So stationary states are energy eigenstates where the time evolution is just given by this exponential factor. Okay, so, okay. And so, so there was a question in the midterm about stationary states. And essentially, what this analysis shows, let me make a comment. The comment is that if we are able to solve the Schrodinger equation for the stationary states, which is equivalently, if we are able to solve, the Schrodinger equation, the time-independent Schrodinger equation, then we can write down the time evolution of any state. Okay? So let me just demonstrate the statement. Let me just first reread the statement. The statement is that if we are able to solve this equation, we are able to find any solution of the Schrodinger equation. Okay? What does this mean? So what it means is the following. So we have the time-independent Schrodinger equation, which is this guy. So suppose we solve it. So the solutions are going to be of this form, psi of e of x, right? These are the eigenstates of H. Okay. And then we can say how psi of E will look like at any future time. At any future time, it's going to look like E to the power minus I by H bar, the time evolution. So this is a time evolution operator acting on psi E of X, right? Which is at time 0. Remember that? And of course, H, if H acts on this, what does it give? So this will give E to the power minus I by H bar E of T psi E of X. So if you're not sure about this step, let me show it to you. This thing is nothing but E to the power minus I by H bar. H hat of T is 1 plus minus I H bar. H of T. I think I didn't write the minus sign over there. I made a mistake here. Let me make sure I correct that. So yeah, there should have been a minus sign here, right? Minus sign here. Yeah. So, and then the next term is minus I by H bar squared by factorial of 2, H squared, T squared, so on and so forth. When this operator acts on this state, this just gives you this state back, right? So E to the power minus I by H bar, H hat of T acting on psi of E, X at time 0. This term just gives you psi E at X of time 0. The second term gives you minus I H bar. H is now replaced by its eigenvalue, E. So there's ET psi E of X of 0. This guy, H acts on this twice. So it gives you 2 factors of the eigenvalue. Right? And similarly, all the other terms will give you higher factors of the eigenvalue. So you can then sum this series up and write it as E to the power minus I by H bar. And where the operator was, you just have the eigenvalue. Okay, is this clear? How we went from this point to this point where this was replaced by the eigenvalue?
That's because psi E is an eigenstate, right?
Yeah, exactly. So, if you have any function of the Hamiltonian operator acting on the eigenstate, then the result is that same function, but the Hamiltonian operator replaced by the eigenvalue. Okay? And we are just choosing a particular function here, which is E to the power minus I by H bar, H of T. Okay? If it's a polynomial function, this is true. Or even an infinite series, which is what we're doing. Okay, so what we have done is that we have shown that for any energy eigenstate given at some time 0, if we multiply it by E to the power E by I by H ET, we get the state at a future time. But we also know that given any state psi, let's call it something else. Let's call it phi. Any state phi at time x can be expressed in terms of the energy, the eigenstate of a Hamiltonian operator or a Hermitian operator. So we can express this in terms of a linear combination of these guys. Let me call them psi En. N is an index for the different energies. Okay, right? We write this, we can express any state like this. If you say, okay, if I give you this state, how do you find this linear combination? Well, you just find this. You just take psi e of n, phi of x. You take the inner product, and that's just Cn, right? Because these guys set an orthonormal basis. So any wave function at time t0 can be expressed in terms of the energy eigenstate at time t. Then so I want to know what the future evolution of the state is. So I want to know what phi is at time t. Then I apply the time evolution operator on phi, which by definition should evolve any state to future. And then if I write this in terms of its expression, in terms of linear combination, we see u of t, there's a summation over n, Cn are constants, and then we have, inside we have psi En x of 0, and then we bring this inside. These are just constants, so this thing doesn't act on them. So we get summation over n, and then we have a C of n, and then this thing acting on this gives me e to the power minus I by h bar, the energy En t psi of En x of 0. And this expression gives me the time evolution of any state at a future time. So I just wanted to show you how, if you are able to find this state for every energy eigenvalue, then you have solved the problem. You know everything about the system, okay? Because you can work out the time evolution of any state. Okay, so this is our discussion about stationary states and how they can be useful, okay? So we are slowly going towards a more concrete problem solving. Today it's still very abstract, but pretty soon we'll be dealing with the nitty-gritty of one-dimensional, very concrete one-dimensional system. Today we did discuss a concrete system, which was the free particle, right? And we found some interesting stuff there as well. Okay, before I move on, any more questions? This is not easy, okay? This is not easy. This is not something you will be able to absorb in one day or even one course. So, you'll have to come back to this again and again. If you're a physicist, throughout your life.